In this lecture, we will continue our talk about the properties of the CTFT. So we'll go over more properties of the CTFT and work some examples. Let's start with the first example here, which asks to find that the CTFT of a signal that is x1 of t, which is a function of another signal, which is x of t. So x1 of t is x of 1 minus t plus x of minus 1 minus t. So to solve this problem, we're going to try to look carefully at how x1 of t is written as a function of x of t. Now, maybe the first kind of thing that we notice that there is a negative sign behind the t. So it's not a simple shift. You're flipping t around the y-axis. So let's rewrite this in a way that we can kind of model this flipping and then the shift. So we can write this as x of, let's say, minus t. Let me use a different color here. Plus 1. And then let me go back to blue and then plus x of minus t minus 1. So I'm going to take, maybe call it y of t. So let's call y of t is x of minus t. So this is going to be equal to y of t plus 1 plus y of t minus 1. Now, in this way, I can use the time shift property, and I can write that x1 of g omega is equal to e minus g omega times y of g omega plus e j omega y of g omega. And now you can take y of g omega outside, and then this is going to be equal to 2 cosine omega y of g omega. Now the question is, what is y of g omega as a function of x g omega? So now if I go back to the definition of, so this is time reversal, so I'm flipping the time axis. So here, if I apply the formula, so y of j omega is the integral of y of t e minus j omega t dt, right? So this is equal to the integral of, so here minus infinity plus infinity, so of x minus t e minus j omega t dt, right? Now if I do a change of variable, which is tau equal to minus t, so here I'm gonna have to flip the boundaries, but dt is equal to d tau is equal to minus dt, so everything is going to cancel out. So the boundaries are going to stay the same, minus infinity plus infinity, and this is going to be equal x of tau e minus j omega t, so this is going to be j omega tau d tau. So this is equal to the DTFT of x, but where omega is replaced by minus omega. So this is x of j omega minus j omega. So if I go back to my main calculation here, so I would get equal to 2 cosine omega x of minus j omega. And this slides give a more detailed description of what's going on here. And then you get the same result here. So we're using two properties: the time shift that we saw before, and the time reversal property, which I actually derived in details in the previous slides. The second example is to find the CTFT of a signal x2 of t as a function of x of t, where the relationship between x2 of t and x of t is the following. So x2 of t is x of 3t minus 6. Now you can see here, you're going to have to use the two properties. One is the time scale, so here you're scaling by 3, and the shift. So we can write this expression as x of 3 times t minus 2. So we have two transformations. First, we're doing a scale by 3, and then after that we're doing a shift by 2. So if I try to write this down, so let's take so f of x3t. If you remember from the time scale, it's going to be 1 over 3. This is x of j omega by 3. So again, there's a dual kind of effect. If you compress in the time domain, you're expanding in the frequency domain. And then when you do the shift, so this is going to be 3t minus 2. You're doing a shift by 2, so maybe here, no. So here it's going to be e j2 omega by 3 x of j omega by 3. And this is x of x2 of j omega. So that's the relationship between the two CTFTs. Actually here I made a typo, so this should have been, there's a minus sign here that is missing, because what we got here with the shift is by a value of 2, so it's e minus j 2 omega. So what we did is first we did the time scale and we found the CTFT of x of 3t, which is this, and then we did the shift. Now you may be tempted to do these steps in reverse, meaning first do the shift and then do the time expansion, multiplying by 3, and then you get a different result. So you have to be careful that the second way of doing it is not correct, because here when you do the time shift, or the time scale, you're just expanding the axis t, so you're doing 3 times t only, and doesn't multiply the delay. So this is actually f of x of 3t minus 2. So you're just expanding the t-axis. So this slide explain how you could fix this. If you decide to do it the other way around, the second way, you have to add an additional delay, so you can take a closer look at these calculations in the slides. But what is important is what I'm going to tell you in the next slide. So the rule here to remember is that if you replace x of t by xt minus 2, this means that the delay is represented by, instead of t, replacing it by t minus 2, and the time expansion, instead of, you replace t by 3t, but this does not affect the delay. So this is why when you do the transformation t to 3t, it doesn't affect the delay of 2 in our example. If you are confused about these things, I think maybe going back to the first principle, or back to the basics, and trying these expressions, the formulas may help you. The next problem is about finding the CTFT of the second derivative of x of t minus 1. So to solve this problem, first we have to account for the delay of 1. So if we define y of t to be x of t delayed by 1, this will give us that y of j omega, so this is y of j omega, is equal to x of j omega times e minus j omega, since here there's a factor 1, which is delay 1. Now we have to apply the differentiation property. So every time we differentiate, we're multiplying by j omega. So we're differentiating here j omega, so d of dt of y of t, which is x3 of t. First we differentiate j omega, we differentiate y of t, which correspond to multiplying by j omega times y j omega. So this is going to be equal to j omega times e minus j omega x of j omega. And then when we differentiate the second time, is the same principle again. So we have to multiply by another j omega. So it's going to be j omega square, e minus j omega x j omega. So in the end, it's going to be minus omega square, e minus j omega x of j omega. So in the end, you could have easily maybe seen this without going in such details in the steps. So this represents j omega square, which is 2 times differentiation. And this part here represents the delay. The last example I want to do in this lecture is application to LTI systems. Here the LTI system is a continuous time system characterized by the following differential equations. So we have the system, the input, which is x of t, is related to the output y of t by the following differential equation, and the question is to find the transfer function h of g omega and find the impulse response of this system. Now to find the transfer function hg of omega, you should remember that hg of omega is the output divided by the input. And then what we have to do is take the CTFT on both sides, and due to linearity, this amounts to taking the CTFT of each term separately. And we just computed the CTFT of d square, or d2y of t divided by dt square. So this is going to be equal to j omega square yj of omega, because we did the derivative twice, plus 4j omega y of j omega, plus 3 yj omega. And here we did the derivative once, so we multiply by j omega times xj of omega plus 2 xj of omega. Now, when we put everything together, we get the transfer function of the system, which is j omega plus 2 divided by j omega squared plus 4j omega plus 3. Now, to find the impulse response, we have to find the inverse CTFT of this formula. To find the CTFT of this formula, first, what we had in the denominator here, we had a second degree equation or quadratic equation. So we find its roots, and then we can write it as j omega plus 1 times j omega plus 3, and now we can do a partial fraction expansion. So we can write h of j omega as 1/2 j omega plus 1 plus 1/2 j omega plus 3. And now from the examples we've seen before, this is h of t here is equal to 1/2 e minus t, so it's an exponential with term 1 here, u of t plus 1/2 e minus 3t u of t, so 3 is coming from here. And this brings me to the end of this lecture.